Welcome to Theory of Computation. This is lecture number 5. In the last lecture, we looked at various examples of Turing machines. We took some languages and then we designed Turing machines that recognize exactly those languages. The idea of last lecture was to familiarize you with the concept of Turing machines and to tell you what are the tricks and methods that are used for designing various Turing machines. In the last lecture, we started discussing some variants of Turing machines. That's what we will continue today. Today, we will look at some variants of Turing machines. We will talk about K-tape Turing machines and K-head Turing machines. Other than that, we will also look at another model of computation called enumerators. Then we will show that K-tape Turing machines are equivalent to our good old one-tape, one-head Turing machine, the simplest Turing machine that we can think of. Similarly, we will show that enumerators capture the same languages as one-tape Turing machines. In order to do that, we will have to look at a very interesting technique called dovetailing. So, let us begin today's lecture. We start by looking at a K-tape Turing machine. Here's a picture of a K-tape Turing machine. As you can see, this Turing machine looks like an ordinary Turing machine except that it has K-tapes. There are K-heads which are allowed to move independently over the tapes. One of the tapes is designated as the input tape. In order to give some input to this Turing machine, we will write the input on the input tape and the machine will be in the start state. It will start computing, and the way it takes a step is by observing all the K symbols that are currently under its tape heads. The machine then decides to take a single step. A single step consists of deciding what to replace the current symbols with, and for each head it decides whether that head is going to move left or right. This is evident in the transition function. As you can see, the transition function is a function from Q cross gamma to the K to Q cross gamma to the K LR to the K, which means that the decision for the step is made by looking at all the K symbols that are currently being scanned. Furthermore, the machine decides to move into a new state. It also decides for each symbol what to replace it with, and for each head whether it will move left or right. K-tape Turing machines, let us say that we are talking about a 50-tape Turing machine. We have a Turing machine which has 50 tapes instead of one. From the surface, it looks like this is a much more powerful Turing machine than a single-tape Turing machine. Well, a very interesting question is, can a K-tape Turing machine accept a language which is not accepted by a single-tape Turing machine? Let us go back and think a little bit about how we have added power to various models of computation. In your automata classes, you must have studied DFAs, deterministic finite automata. These are machines which don't have any memory in the sense that they are not allowed to write anything on the tape. They can only read the input. They cannot write on their tape. Well, these machines, as we know, accept only regular languages. After that, you must have studied the concept of context-free grammars and push-down automata. In push-down automata, the machine has an extra memory which it comes in form of a stack. Non-deterministic push-down automata accept what are called context-free languages, languages which can be generated by context-free grammars. And as we know, regular languages are a proper subset of context-free languages. This tells us that if we take a DFA and we add a stack to it and make a push-down automata, that is a more powerful model of computation. Another thing for you to notice would be if we look at the language A to the N, B to the N, C to the N, you must have learned in your automata class that this is not a context-free language. However, it is very easy to design a Turing machine which accepts this language. So, Turing machines are strictly more powerful than non-deterministic push-down automata. They can accept languages for which there is no non-deterministic push-down automator. Well, we can ask the same question about two-tape Turing machines. Can we make a two-tape Turing machine which accepts a language which cannot be accepted by any one-tape Turing machines? This question asks if two-tape Turing machines are strictly more powerful than one-tape Turing machines. We can also ask the same question for more tapes. For example, we can ask if 50-tape Turing machines are much more powerful than a single-tape Turing machine. So, does adding more tapes to a Turing machine give it any extra power? The answer to this question is no. You can add as many tapes as you want to your Turing machine. It does not become more powerful than a single-tape Turing machine. What does this really mean? What it means is, suppose that somebody has designed a k-tape Turing machine, let's say a 3-tape Turing machine. And this machine, we give some input to this machine, and that machine accepts or rejects that input. So this machine recognizes a particular language. Well, what we can do is we can find another Turing machine which is only a single-tape Turing machine which will accept exactly the same language. So adding more tapes to the Turing machine does not give it any extra power. Every multi-tape Turing machine has an equivalent single-tape Turing machine. This is the theorem that we will start by proving today. How can we prove such a theorem? Let us first intuitively think about it. Suppose somebody has, for simplicity, say a 2-tape Turing machine. This Turing machine accepts some language. So if we give it some input, it starts computing, and then it may reach an accept or a reject state. What we want to do is instead now make a single-tape Turing machine which accepts exactly the same strings as this 2-tape Turing machine. Well, how can we do the same job this 2-tape Turing machine is doing on a single tape? The answer to that is, what we can do is we can take the contents of the first tape and put it and write them down, followed by the contents of the second tape. That way, if we had 2 tapes, we could simply write the contents of both of these tapes on a single tape. We can continue to do that. It doesn't really matter if somebody has a Turing machine which has 500 tapes. We can write the contents of the first tape followed by the contents of the second tape and so on, and thereby writing the contents of all these tapes on a single tape. This would be the technique that we would use to show that for every k-tape Turing machine, there is an equivalent single-tape Turing machines. Let us look at this in more detail. Let's look at the following picture of a multi-tape Turing machine. This Turing machine has 3 tapes. How can I describe the configuration of this Turing machine? The configuration of this Turing machine is described as follows. The machine is in state Q3. On the first tape, it has A, B written on it, and the third A is being scanned. On the second tape, it has B, B written on it, and the third A is being scanned. Similarly, on the last tape, it has B written on it, and the second A is being scanned. I can write this configuration linearly as Q3 followed by a hash sign, followed by AA, followed by A with a dot, AB, followed by a hash sign, followed by BAA, then A with a dot, followed by a B, followed by a hash sign, followed by A with a dot, AB. Now the main point is that I can write this configuration linearly on a single tape. The method of writing a configuration on a single tape is as follows. What I can do is write down the first state followed by a hash symbol. Then I can write down the contents of the first tape followed by a hash symbol. Then I can write down the contents of the second tape followed by a hash symbol, and so on for all the tapes. In the end, I go through what I have written down and place a dot on all the symbols that are being currently scanned. Suppose now that I have only a single tape and I want to know what a multiple tape TM will do if it were given an input W. What I can do is I can write down Q0 followed by a hash sign followed by W prime followed by a hash sign followed by a box with a dot on it, and so on. This denotes the initial configuration of the machine M on the input W. Here, W prime is the same string as W, except for the first character has a dot placed on top of it. Now I can keep scanning the entire tape to find out on which symbols dots have been placed, which will tell me which symbols are being currently read by the Turing machine M. After that, we can make a second pass over this single tape and make all the modifications that M would have done in a single step. Let us be a little more formal with this proof. What we have seen right now is how to convert description or configuration of a multi-tape Turing machine into a single tape. How can we write down the configuration onto a single tape? Now let's see how we can simulate the computation of M using this single tape. Suppose we are given a K-tape TM M, we describe a single tape TM S. S is going to simulate M by using only one tape. The description of S is as follows. Let us say that the input to M is W, which is equal to W1, W2 up to Wn. What S is going to do is put its tape into the following format. We will have a hash sign followed by W1 with a dot on top of it. Then we will write W2 up to Wn. Then there will be another hash sign and there will be a box with a dot on top of it. There will be actually K-1 such things over there. This shows that the machine M is actually reading the first input symbol and all its other tapes are blank. To simulate a single move of M, S will scan its tape from left to right in order to determine the symbols that are placed under its virtual heads. Here, you see the Turing machine S has only a single head, whereas the Turing machine M has K heads. So by placing dots on the symbols, the machine S has created virtual heads, and therefore it can try to simulate the behavior of the machine M. If at any point the machine has to move the head to the right of a hash sign, that is, M is moving to a previously unread blank, then S inserts a box with a dot on top of it by shifting all the symbols to the right. Now if S continues doing this, so what S does is it scans its tape every time to find out what are the symbols that are being read by the Turing machine M currently, and then in the next pass it makes the changes that M would have made. It continues doing this, and if M ever reaches an accept state, S is going to accept. If M ever reaches a reject state, then S is going to reject. Let us look at the description of this Turing machine S in little more detail. First of all, what we have to understand is S is a Turing machine that is trying to simulate the behavior of the Turing machine M. And it's doing that by placing all the contents of the K tapes of M on its single tape. Let us say that we have a 3-tape Turing machine M and we give it the input AABB. The initial configuration of the machine looks like this. This configuration will be written on a single tape of S as Q0 A dot ABB followed by a hash sign followed by a blank with a dot on top of it, followed by a hash sign followed by a blank with a dot on it, followed by a hash sign. As you can see, here the dots are telling us which symbols are being scanned, and the hash signs are separating the various tapes of this Turing machine. Now suppose that delta of Q0 on A blank blank was equal to Q2 BAC RRR, which means if the Turing machine M would have gone to state Q2, it would have replaced the A with a B, it would have replaced the first blank with a C, it would have replaced the blank on the third tape with a A and move all heads to the right. Then S will change its tape contents to become BA.BB followed by a hash sign, followed by C blank dot, followed by A blank with a dot on top of it, followed by a hash sign, which represents the new configuration of this 3-tape Turing machine. Let us look at the 3-tape Turing machine and see what it would have done. As you can see, this Turing machine has moved all its 3 heads and changed the contents. However, S has codified this configuration on a single tape. Now let's see what will happen if this 3-tape Turing machine were to take one more step. Suppose that delta of Q2 comma A blank blank was equal to Q3 CBB RLR. This means in this case the Turing machine will move the first and the third head to the right, but the second head will move to the left. In this case, the machine will end up in the following configuration. Let us look at the picture of this configuration. As you can see, the machine has moved the first head and the third head to the right, and it has moved the second head to the left. S will codify this configuration on its single tape as follows. It would be BC, B followed by a dot B, hash C with a dot on top of it B, followed by hash AB and a box with a dot on it. As you can see, this correctly codifies the configuration of a 3-tape Turing machine. So, in order for S to simulate the behavior of this Turing machine M, it will have to do a lot of work. Every time M takes a step, what S has to do is make one pass over its tape and find out which are the symbols being scanned, and then make another pass over the tape and make the changes that M would have made to its 3 tapes. So S is simulating the behavior of M, and for each step of M, it has to do a lot of work. However, the computation of M is being replicated by the computation of S. So if M accepts a particular string, S will also accept that string. On the other hand, if M rejects a particular string, then S will reject that particular string. This recipe of making this simulator works for any Turing machine M, K-tape Turing machine M that you gave me. Therefore, I have shown that for every K-tape Turing machine, there is an equivalent single-tape Turing machine. Thus, we have proved our theorem. Every multi-tape Turing machine has equivalent single-tape Turing machines. A few words about this theorem. Notice that we have only given a high-level description of S. You should convince yourself that given any K-tape TM, you can come up with an exact and formal definition of S, which means you should convince yourself that you can fill out all the details of this proof. Note that the work alphabet of S is going to be much larger than that of M. We will need to include all the work symbols of M into the work symbols of S, and we would duplicate these work symbols and put a dot on top of them, and also include those as work symbols of S. We would also need to include the hash sign to be another work symbol of S. The third point to notice is that the Turing machine M takes a single step, whereas S has to do a lot of work, namely make 2 passes over its tape in order to simulate a single step of M. So you can say that the Turing machine S is not more powerful than M because it works very slowly. It is not very efficient. However, in computability theory, we are not going to be concerned with efficiency. That concern will come later when we start studying complexity theory. So although S may be simulating the behavior of M very slowly or by doing a lot of work, but it will accept exactly the same strings as M. So the language of S is going to be exactly the same as language of M. This means for every multi-tape Turing machine, there is a single tape Turing machine that accepts the same language. Well, we can look at some other variants of Turing machines. For example, we can be a bit fancy and say, Well, let's think about a Turing machine which has only one tape with several heads. So we have a K-head Turing machine. Let's look at a picture of a K-head Turing machine. As you can see in this picture, this Turing machine has a finite set of states. It has only one tape. However, it has several heads that are simultaneously reading and writing on different parts of its tape. These heads are allowed to move independently. Well, are K-head Turing machines more powerful than a single head, single tape Turing machine? I mean, that is a very interesting question. Does adding a lot more heads to a Turing machine give it any extra power? It is your homework to show that that is not the case. That for every K-head Turing machine, you can find a single tape, single head Turing machine that accepts the same language. The basic idea is, once again, follow the same strategy as we did for the previous proof. Some details have to be worked out and they are slightly different. However, the basic outline will be the same. What you will do is you will take the K-head Turing machine and try to create a one tape, one head Turing machine that simulates the behavior of this K-head Turing machine. This simulator once again will be very slow. It will have to make passes over its tape in order to simulate a single step of the K-head Turing machine. However, it will accept the same language as the K-head Turing machines. I will leave the details of this theorem for you to prove. So, we've shown that K-tape Turing machines are equivalent to a single tape Turing machines. Well, can this theorem help us in any way? Does it make our lives simpler? You should always ask yourself whenever you prove a theorem is, when can I use it? So, what is the use of proving this fact? It turns out that for many languages, it is much easier for us to describe a 2 or a 3 tape Turing machine rather than a single tape Turing machine. What we can do is, if somebody gives us a problem, a language, and asks us to design a Turing machine for it, we can design a 12 tape Turing machine, and that would show that this language can be recognized by a Turing machine, a 12 tape Turing machine. Then we can apply this theorem to actually claim that this language is also recognized by a single tape Turing machine. This will make our lives quite simpler. Let's look at an example like that. Let us look at this language L, which is the set of all W followed by a hash sign followed by W, such that W is a string over 0 ones. This language is decidable. Well, you can design a Turing machine which accepts this language. The basic problem is, you're given a string followed by a hash sign followed by another string, and your Turing machine has to make sure that these two strings are the same. What we can do is we can shuffle between these two strings and compare them symbol by symbol and make sure that they are the same string. So you can design a one tape Turing machine which will accept this language. On the other hand, it's much more natural and simpler to design a 2 tape Turing machine that accepts this language. Basically, the problem is that you're given a string over 0 ones followed by a hash sign followed by another string over 0 ones. So you're given W1 followed by a hash sign followed by W2, and you would like to know if W1 is equal to W2. Well, what we can do is, in a 2 tape Turing machine, scan the input once and make sure that it's of the correct form, and we take all the contents that come after the hash sign and copy them off on the second tape. Now, on the first tape, you have the first string, and on the second tape, you have the second string. And we would like to know if these two strings are equal. Well, since we have 2 tapes, we can place the 2 heads to the left and start matching these characters one at a time as we go to the right. If all the characters match, we will accept, otherwise we will reject. This is a much more natural way of solving this problem rather than shuffling left and right using a single tape. So, for many problems, it is much easier to describe a multi-tape Turing machine rather than a single tape Turing machine. Of course, After we have described a multi-tape Turing machine, we can invoke our theorem and say that there is also a single tape Turing machine that accepts the same language. Let us describe this two-tape Turing machine and see how easy the description of this two-tape Turing machine is. The description of this Turing machine is as follows. In the first pass, we make sure that the input is of the form W1 hash W2. In the second pass, we copy the contents of after the hash symbol to the second tape. Now we bring both the tape heads all the way to the left. Now we match the symbols of W1 and W2 one by one and make sure they are equal. Of course, this is a much more natural way of solving this problem. So this two-tape Turing machine is, the description of this is much simpler than that of a one-tape Turing machine. Let us look at another model of computation. This model of computation will be called an enumerator. What is an enumerator? An enumerator is going to be a device which will take no input. When we turn on this enumerator will have a work tape and it will start working, and it will only produce outputs. And the output would be of the form a string followed by a hash sign, followed by a string, followed by a hash sign. You can imagine an enumerator as being a program that when you run only starts producing an output, so it just keeps printing things onto a piece of paper. What we would like to do is to understand what are the languages that can be enumerated by these things called enumerators. An enumerator will just simply have one work tape and one output tape. It will have no input tape. It will start in a state Q0 and then it will start working. It will look at the current symbol that it's scanning on its work tape, and then it will decide to change its states, replace the symbol that is currently being read, and it may also decide to write something on the output tape. Once it's written something on the output tape, it's not allowed to move back. It's not allowed to erase anything that it has written on the output tape. Let's look at a picture of an enumerator. As you can see in this picture, what we have is a finite set of states. There is a work tape and there is an output tape, which in this picture is shown by a printer. This enumerator will, when it's turned on, it will start working and then producing some output. We define the language enumerated by this enumerator to be the set of all strings that it writes on its output tape. So what you do is you turn on this enumerator and it starts producing outputs. It starts writing a string and another string and another string. And if you collect the set of all these strings, that is called the language enumerated by these enumerators. This model of computation is very, very different from a Turing machine. Turing machine is a machine that accepts or rejects a given input. An enumerator, on the other hand, does not take any input. It only produces an output. They are very different models. However, they are also equivalent in the following sense. What we will show is that suppose you have an enumerator and it enumerates some language L. We will be able to make a Turing machine M that will accept all the strings that are enumerated by this enumerator E. So given an enumerator that enumerates a language, I will be able to make a Turing machine that accepts exactly that language. On the other hand, we will also show that if a language is accepted by a Turing machine, then we can make an enumerator that enumerates exactly the same language. So this will show equivalence of these two models of computation. The theorem that we want to prove is that a language is Turing recognizable if and only if it is enumerated by some enumerator. This theorem has two parts. The first part says that suppose you have an enumerator E that enumerates some language L. then what we can do is we can find a Turing machine which accepts this language L. The second part of this theorem is the other way around. Suppose that you give me a Turing machine M which accepts some language L, then what we will have to show is that there is an enumerator E that enumerates exactly the same language as L. Let's start by doing the easier part first, and let's think about it intuitively. Suppose that you have an enumerator that enumerates some language. How can you make a Turing machine that accepts all the strings that are enumerated by this enumerator? Let's say that you give this Turing machine W as an input. This Turing machine would want to find out, or we would want to find out, if this string W is ever enumerated by the enumerator or not. So, in order to do that, the only sensible thing that comes to our mind is we can turn on this enumerator and wait for the string W to appear on its output. So the working of this Turing machine will be as follows. This Turing machine will have all the functionality of the enumerator E built into it. It would be doing this, it would have a work tape which would be the same as the work tape of the enumerator E. Furthermore, the output tape of the enumerator will also be a work tape of this Turing machine M. This Turing machine M will run the enumerator E till it produces an output. Once it produces an output, the Turing machine will take its own input, which is W, and try to match it with the current output that was produced by this enumerator. If it ever matches, the Turing machine will accept W, otherwise it will continue and run the enumerator again till it produces the next output. So the informal description of this Turing machine M is as follows. On input W, take the enumerator, put it in the initial configuration and start running it. As it produces its outputs, match them with the input. If you ever find a match, accept. Otherwise, continue. As you can see that we have described this Turing machine M, which is only a recognizer. This is not a decider. In this case, suppose the Turing machine gets an input W, which is never enumerated by this enumerator. The machine will continue to run this enumerator, hoping to see this input W, which will never arrive. And therefore, this Turing machine would not halt in this case. That's why this Turing machine is only a recognizer, but not a decider. So, this was quite easy. Now, let us try to prove the other part of this theorem. The other part says that suppose you have a Turing machine M that accepts some language, then we can make an enumerator E which will enumerate all the strings in this language, exactly those strings in this language. Well, suppose, let's first think about it intuitively. Suppose somebody has given you a Turing machine. So this Turing machine is capable of accepting, rejecting strings. So you can give it a string and you can run this Turing machine on it, and this Turing machine may accept this string, reject that string, or may loop forever on that particular input string. What we want to do is we want to enumerate all the strings that are accepted by this Turing machine. The first idea that comes to our mind is what we can do is we can go over all the strings in lexicographical order and run our Turing machine M on this string X. If this machine accepts X, we can output this string and output it on the printer. So that would be our first description of this attempt at making this enumerator. So formally, the enumerator is described as follows. Let x1, x2, x3 all the way up to xn be strings in lexicographical order. Run the Turing machine M on xi. If M accepts xi, output xi. Will this work? will this enumerate all the strings that are accepted by this Turing machine? Well, let's think about it a little bit. Let us consider a Turing machine that has the following properties. This Turing machine M accepts the string epsilon, the empty string. It rejects 0. It accepts 1. It loops forever on 0, 0. That means if we give it the input 0, 0, the Turing machine simply computes forever and it does not reach an accept or a reject state. And it accepts the string 0, 1, and I have not specified what it does on the other strings. What would happen if we were to run our enumerator, which we have described before? Well, our enumerator will start enumerating the strings in lexicographical order, but before outputting them, it will run M on that string. If M accepts, it will output that string. So it will start with the empty string. It will run this Turing machine M on the empty string. Since this string is accepted, it will output the empty string. Next, it will move on to 0. It will run M on the input 0. M will reject this string, so E will not output this string. So that's very good. 0 was not in the language of M, and our enumerator is not going to output it. The empty string was in the language of M, and our enumerator outputted that. Then it would run M on 1. Since M accepts 1, it will output 1. So that's also very good. So far our enumerator seems to be working fine. But here comes a problem. The next string in lexicographical ordering is 0, 0. When our enumerator runs M on 0, 0, this machine does not halt. It will neither reach an accept state nor it will reach a reject state. So our enumerator will not output 0, 0. That seems fine because 0, 0 is not in the language of M. However, if you would notice that 0, 1 is in the language accepted by M. But since our enumerator is never going to get to 0, 1 because when it started running the machine M on 0, 0, the machine went into an endless loop. Thus, 0, 1 never gets an opportunity. So this enumerator will simply enumerate epsilon and 1, and it will never enumerate 0, 1. So this enumerator is not going to enumerate the language accepted by this Turing machine M. What went wrong? Well, in this case what happened is the string 0, 0 took up all the resources of this enumerator, and therefore the string 0, 1 never got an opportunity. The enumerator was going through all the strings one by one and checking if they are accepted by the Turing machine. However, when it came to the string 0, 0, the Turing machine simply never returned. It went into infinite computation, and therefore the enumerator never checked 0, 1, which should have been enumerated. Well, can we actually design an enumerator which can overcome this kind of a problem? So what we want to do is we want to design an enumerator which will enumerate all the strings that are accepted by this Turing machine M. For that, we will use a very interesting technique which is called dovetailing. The basic idea behind dovetailing is that we will not give infinite amount of time to any string. What we will do is we will run our Turing machine on a given string for a limited amount of time. If the Turing machine accepts that string, we will output it. On the other hand, if the Turing machine does not accept the string in that stipulated time, we will move on to the next string. However, we'll come back to this string again and give it more time. This way, we will be able to enumerate all the strings that are enumerated that are accepted by this Turing machine. Let's look at dovetailing in a little more detail. Here is what we do. The technique of dovetailing goes as follows. The enumerator is going to run in phases. In phase number 1, it will run M on the first string x1 for 1 step. In phase number 2, it will run M on x1 for 2 steps, and it will also run m on x2 for 2 steps. In phase number 3, it will run the Turing machine m on x1 for 3 steps, on x2 for 3 steps, and x3 for 3 steps. So in the phase k, the enumerator will run the Turing machine m on the string x1 for k steps, x2 for k steps, all the way up to xk for k steps. If any of these strings are ever accepted by this Turing machine, the enumerator will simply output those strings. Let us think about what will be the output of this enumerator. What are the strings that will be outputted by this enumerator? Let's say that I have a particular string xi which is accepted by this Turing machine. So this string xi is accepted by this Turing machine, and we have no idea how many steps the Turing machine computes before accepting this string. Let's be more concrete. Let's look at 0, 0. Let's say that the machine takes 300 steps to accept 0, 0. Well, then my claim is that this enumerator in its 300th phase will output 0, 0 surely. Of course, in the 300th step, this string 0, 0 will be outputted because the enumerator runs m on the first 300 strings for 300 steps. So after the 300th phase, it's giving enough time to this string to be accepted by the Turing machine, and it is outputting all the strings that are accepted by this Turing machine. Let's note that if the Turing machine does not accept a string xi, then it will never be outputted by this enumerator. There is one more interesting thing to note. Suppose that there is a string x on which the Turing machine computes forever. That will also be never outputted by this Turing machine. You can think about dovetailing as time sharing. What is happening is each single string is being given a small time slice. Thereby, if there is a particular string which is making the Turing machine go into infinite computation, still that string is not preventing other strings from being enumerated, since the Turing machine only gives a finite amount of time to each string and then moves on to the next one. Therefore, if a string is taking forever, it does not prevent other strings from being outputted by this enumerator. So this technique, dovetailing, allows us to prove this theorem. You will notice that if you use this technique, dovetailing, the enumerator is actually doing a lot of computations which seem unnecessary. However, by doing these extra computations, it is making sure that it enumerates all the strings that are accepted by this Turing machine m, and it does not run into a problem. That means if the Turing machine is going into infinite computation on a given string, it can still give the next string some chance. Let's look at an example which is much more concrete and explains this concept a lot more. Let us say we have a Turing machine m, and it has the following behavior. When we give it the input epsilon, it accepts the input in 3 steps. When we give it the input 0, it goes into an infinite loop. When we give it the input 1, it accepts the input in 17 steps. And when we give it the input 1, 0, it accepts the input in 12,000 steps. In this case, if we use the technique of dovetailing, then the string epsilon will be outputted in the second phase of the algorithm. That's because in the second phase, the enumerator runs m on the strings epsilon and 0 for 2 steps. So epsilon would be accepted and outputted in this phase. The string 0 will never be outputted by this enumerator. The string 1 will be outputted in the 17th phase by this enumerator. On the other hand, the string 10 will be outputted actually in the 12,000th phase of this algorithm. So this enumerator will be enumerating all the strings that are accepted by this Turing machine M. What we have done now is shown that the languages accepted by Turing machines are exactly the same as the languages that are enumerated by enumerator. Thus, these two models of computation are the same. They capture exactly the same languages. Well, we are going to prove another theorem about enumerators, and this theorem is going to be also very interesting. As you know, we have certain Turing machines that we call deciders. These are Turing machines that either accept the input or reject the input. They never go into an infinite loop. We will show that if we have a Turing machine M which decides a language, then there exists an enumerator that enumerates that language in lexicographical order. So we will be able to show that we can build an enumerator that outputs the strings of that language in sorted order. Similarly, we will show that if we have an enumerator that enumerates a given language in sorted order, lexicographical order, then we can actually make a Turing machine that accepts that language and halts on all inputs. So if an enumerator enumerates a language in lexicographical order, then we can make a decider that accepts that language. I hope you have enjoyed this lecture, and I also hope that you've been doing the exercises that are being assigned to you in the homeworks. I will see you next time. Thank you and goodbye.